Okay, great. Hi, everyone. Yeah, as Steph says, I'm Sam Seccombe, working at ZSL. I've spent the last 3 years developing the second incarnation of Instant Detect. And this is a satellite-connected wildlife monitoring and threat detection system. I'm not actually going to talk to you much about this today, though, as there are quite a few blogs on Wild Labs that describe what the system does. However, when developing Instant Detect, I have spent a huge amount of time looking at how different camera traps work, and then even more time designing our own camera trap. Oh, I changed slide. There we go. Great. Before I launch into this talk, though, I want to first quickly caveat that I'm in no way an expert on camera trapping. Fortunately, though, being based across the road from the Institute of Zoology means that I have quite a large pool of very experienced camera trappers to pester and ask questions to. And having seen some of the questions we've already had in this talk and at registration, I'd like to signpost at this point these two documents, WWF's 180-page document on camera trapping, and also the paper, Camera Trapping version 3.0, Current Constraints and Future Priorities for Development in Remote Sensing in Ecology and Conservation, that was linked with this virtual meetup. They're both freely available, and I actually snipped this table out of that paper because it has a lot of common camera trap issues and solutions, and I think they're all very sensible. The reason I bring up this paper mainly, though, is that it breaks down camera trap design into 3 different phases. We have the first phase with the experimental camera traps that use photographic films, which should only take 24 shots. They then say that we're in phase 2 now, which is with these well-provisioned commercial camera traps. And then they sort of look at phase 3, which are ideas for future camera traps. And they describe these as having excellent detection circuitry, resistance to extreme environments, onboard imaging, filtering, wireless transmission of data, and tools for automatic management and analysis of collected images. And so actually, having read this, I realized that I've just spent the last 3 years developing a phase 3 type camera. However, there's no point doing this unless you retain all the performance characteristics of what a user would want from a phase 2 camera. So I'm going to talk about that a bit further now. It was actually, it's a very exciting prospect to design a camera trap specifically for conservationists and not something to be taken lightly. And so I thought that today I'd just share some of these hardware insights which I've learned along the way, because I think if you're going to choose or even build camera traps, they might be quite helpful. And I'm going to cover the following bullet points. So what performance are we talking about when we're using camera traps? And there's actually a lot more than you might initially think. You have sort of passive infrared detection sensitivity. There's the speed of the first image capture. There's the speed of the second and third image capture when you're using bursts. You've got the image resolution. You've got the field of view and the focal length of the lens. You've got the dynamic range, the infrared wavelength and the flash strength that the camera takes. You've got to make sure that the camera is silent and doesn't disturb animals. There's how many batteries should it have in there? What sort of battery chemistry should the camera use? What power usage does the camera therefore need to have? How should you design the controls? And how much can you actually make this thing cost to actually be financially viable? The list just goes on and on. The first thing I started doing was these camera comparison tests. And actually, they do tell you in a huge amount about your camera compared to what other cameras are doing. In these images captured at dawn in Kenya, you can see a leopard being caught by a bushnell at the top, a spartan in the middle, and a reconnax at the bottom. And so the first thing you notice is it's really obvious that the bushnell is the quickest camera here, and it's capturing the leopard in the first, second, and third images, all fractionally separated. Then the spartan wakes up, takes the next image, And these images are already dark and actually quite hard to see. But you can actually see in the middle image the leopard hearing the camera, looking at it, and then breaking into a run. And then at the bottom, we've got the Reconyx, which is obviously the slowest one to detect and wake up. And its images are much more spaced apart. But the image quality is excellent. So what is causing all these differences in performance? So I'm going to start with the passive infrared sensitivity. And I've snipped this picture from trailcamerapros.com website, who I really recommend as quite a useful resource. In this image, they've made it quite clear. They've shown the PIR detection zone of the camera in red, and then in pink, you have the field of view of what the camera can actually see. But the PIR detection zone is wider than the field of view. And so what does this actually mean? Well, what it is actually showing us is that there must be a short delay for the camera to wake up when the PIR sensor is first triggered until the first image is then captured. And so for this camera, the designers expected the animal to walk in from the side and then be captured shortly after entering the image frame when the camera is woken up. However, a downside of this design is that animals that trigger the PIR sensor but remain out of the field of view will cause an empty image, and then you've got to process that in your analysis. In my testing, I found that actually cellular camera traps that then send images captured would appear to be more accurate at capturing animals, as in my test, we got far fewer false images, empty images. But I actually think they achieved this by having a really narrow PIR detection zone centralized in the middle of the field of view. And if you do this, this reduces the number of empty images, because anytime the camera wakes up and triggers, there's going to be an animal right in the center of the field of view. However, though, this means that in reality, animals might have been quite close or actually within the field of view, but not detected. And so therefore, it actually is less accurate at detecting things. There's one camera called Little Acorn, and that actually has 3 PIR sensors with 2 facing outwards, and then the central one, and these wake up the camera, and then the central one, when triggered, will then take the picture. And now this is quite clever, but unfortunately it then uses triple the power for these 3 sensors. So moving into passive infrared sensitivity, as this is another little mystery that's worth understanding. So camera traps use an infrared sensor, which is passive, and it splits into 2 inputs, positive and negative. And in this image, positive is red and green is negative. And then when a detection in temperature is measured at one of these inputs, a voltage spike is outputted. And this therefore means that if the temperature changes in front of the whole sensor, then both the positive and the negative voltage spikes at the same time, and these cancel each other out and you don't get a detection. But if they spike sequentially, you do get a detection. And this effectively makes the sensor a motion trigger. Now it's up to the camera manufacturer to set at what threshold of voltage spike the camera should trigger, and also at how much time should elapse between the positive and the negative trigger to generate an alert. And this is what determines how sensitive your camera is. Some cameras actually allow the user to have some sort of control over this by giving low, medium, and high sensitivity settings. And so in effect, if you're in a very hot country where the background temperature and the animal's body temperature is going to be very similar, you want to increase your sensitivity and have your sensitivity set on high. And in a cold country with a lot of snow, vice versa, have it on low. But just like a camera's image sensor, a passive infrared sensor needs a lens to focus what it's looking at properly onto the sensor. And for this, it uses a Fresnel lens. And this basically just directs all the incoming radiation into the central point. But actually, camera traps use a number of Fresnel lenses all stuck together, as we can see in this picture here. And this essentially causes a number of detection zones to be created. And it's easiest to work this out as if you project it out from the lenses where the image sensor is looking at, onto an image, you see a number of positive and negative sensor zones, the red and the green patches. And so you'd only get a detection if a heat change is detected in the red and then the green sequentially. But the problem is camera traps makers all use different Fresnel lenses. And so the Fresnel zone patterns all vary from camera to camera. The only real consistency that I've seen is that the upper third of the image is unlikely to have the Fresnel lens focus on it, because this reduces triggers by clouds and sun. So I'd sort of caution any camera trap user to look at their Fresnel zones and try to understand exactly where in the picture or in front of the camera they're going to get detections. And this also helps explain why animals walking directly at a camera are often missed. So as we saw in our comparison images earlier on, image quality does matter quite significantly. Most camera trappers I've spoken to would actually rather have a full color image than go into the monochrome of IR night images. And so to do this, you do need a very good image sensor that's going to be good at taking low light images. But another thing that's quite important is the dynamic range in most of the places that people do camera trapping. Dynamic range is the ability to capture details in the dark areas of an image while also capturing the information very clearly in the brighter parts of the image. And this is a very difficult balancing act if you're just doing it with exposure time of the camera. The image on the left here, in the dark bit, there should actually be a hairy pig, but it's almost invisible in the shadows there, as it's trying to capture that water flowing out of the tap. So designing my camera, we found it took a very, very long time to build a really good exposure curve, because you have to take a lot of pictures at a lot of different exposure speeds and add a lot of different light settings. When you think about this, you might think that phone cameras now do this very well, but what they're actually doing to make one picture is taking a burst of images of different exposures and then superimposing the different images on top of each other to make one image. But if we did this in camera traps, it would create a lot more processing. And so fundamentally, it's better to get a really good image sensor, like those used on dash cams. Those are very good because they capture a lot of night detail, but also can deal with bright headlights. The final little area I want to touch on today is the image resolution and read-write speed of cameras. Image resolution has a huge consequence on the read and write speed of a camera. And this in turn affects the speed that the camera can capture images at and the recovery time of the camera. And it also influences the amount of power the camera is going to use. So how does this work? Why does this matter? Well, when a camera is triggered, the SD card is first powered up. And you can see this on the right-hand part of the image. And then some cameras, well, this is a Bushnell's one here, need to read the SD card to work out what file number to give the incoming images. And this takes a little bit of time. You can then see it writing the free images. When a camera actually does power up, though, it will start capturing images in a raw image file format. And then it will cache them into a temporary RAM memory. From this, it will then usually compress the raw images into a JPEG format, add the metadata into the image, and then also add the data bar and the timestamp onto the image. And once this is all done, it will write this onto the SD card. And so effectively, the recovery time of a camera is the length of time that it cannot take images because it's doing this process when it's being constantly triggered. Some cameras will try and do this entire process of writing to the SD card each trigger and will not continue capturing images until the RAM is all freed up. And depending on camera, this can take between 3 to 10 seconds or so for a burst of free images. But other cameras I've seen seem to have a really fast recovery time. But in actual fact, they just have a much larger amount of RAM. So they store more images into this, and then they hope that there's going to be a lull in triggering where they can write them all to SD card. And I've seen that if you constantly trigger a camera with large RAM, at some point the RAM fills up, and then it will take 20 to 30 seconds for all of those images to write to the SD card. So you actually get a bigger gap in your detection. So then coming back to image resolution, this is important because the number of pixels the image sensor has, the larger the amount of data that's going to need to be cached in the temporary memory and then compressed and then written to the SD card. So it's going to take a lot longer. And so I think the megapixel numbers of cameras have been a bit of a red herring for most people in the last few years, whereas 2 to 3 megapixels is usually going to be more than enough for most camera trapping users. And if you're building a future camera trap that's going to send the images, they're going to have to be compressed anyway. So, you know, you're good with 3. And actually, despite advertising, most cameras only use a 3-image megapixel sensor anyway, and then they extrapolate, which is where you subdivide the pixels later to create a higher megapixel count. So here, I think that's interesting. You might not. The last thing to note here is that your camera is only going to be as good as the SD card you put in it. So if you put a really bad SD card in there, it's going to take a lot longer to read and write from it. Therefore, I would recommend using a reputable SD card brand and get the highest read-write speeds that you can afford for it. And for simplicity, if you want to know what that is, if you look for a little C with a 10 on the card, that's a class 10, and that should meet most camera traps' performance needs. Okay, getting there. The last thing I wanted to touch on is the complexities of building a future camera trap, a phase-free camera, if you will. The 3 things I think are key to consider here are the image transmission, the image selection, and then the power usage. So let's start with image transmission. To transmit an image wirelessly across a long distance, the technologies open to you are actually only going to be cellular, satellite, or radio. If only sending the images wirelessly a short distance, you could also use Wi-Fi or Bluetooth. Now, there are advantages and drawbacks for each of these. For example, cellular connections may not be available when you're very deep in the bush, so you might need satellite connectivity. But then satellite transmissions can become very expensive very quickly. Even radio transmissions, you have restrictions on the frequencies you can use and the amount of airtime that a device can legally transmit for, which is known as the duty cycle. And even more confusingly, these rules will change per geographic region. So there's not one-stop shop for this. But it doesn't really matter. Whatever technology you're going to use, you need to reduce your airtime as much as possible so you can reduce your power usage and also your transmission costs. And so the question is, how do you do this? Well, this is done through image selection. We can compress image data, we can strip data out of images, we can even process the images and select which images you want to send and which you should just store. But again, all of these activities are going to use power and processing capacity. On the right here, these pictures of a giraffe were how the first version of Instant Detect did this. It would send a compressed full color image first, and then only the pixels that had changed in the second and third images were then sent. These gray images therefore have significantly smaller amounts of data to send. And then once they got to the end, to your piece of software, where you look at the images would be reassembled using the pixels from the first image. And actually, this was a very useful thing to do because you could use it as a detection method. However, you can imagine the confusion caused if the first image failed to send properly. You just could always grade images, very confusing. So for image detection, we're going to need to use some sort of image recognition algorithm. And these can be very simple, quite complex, but either way, they need to be fast, and the process on the camera needs to be good enough to do this processing, ideally quickly, and also at a low power. And the issue with these image recognition algorithms I've seen is that even the best ones are incorrect some of the time. And so you end up sending an image that you didn't need to send, you waste airtime, you waste power, and the person at the other end who's looking at the images gets fatigued because they just sent another false alert. Right, very, very finally then is power. For me, making camera traps in the future, being low power is absolutely critical. The phase 2 cameras that we get off the shelf now, some are able to run up to 12 months using 8 to 12 good internal AA batteries. And that's quite a target to hit. Obviously, the easiest thing to do here is just strap more batteries onto your future camera. But I don't really believe in doing this because if you do put them internally to protect them, this increases the size and weight of the camera. If you put them in an external battery pack, You've got to connect this with cables, you've got to hide it, it increases the number of expensive connectors you need, and there's all that additional cost of it. Well, I reckon that's me well out of time. I hope that some of what I've said has been helpful and hasn't just been teaching fish how to swim. If you have any questions on camera traps or are interested in learning more about Instant Detect, please do contact me through Wild Labs, where I can be reached quite easily.
That was awesome, Sam. Thank you. Prithvi, do you want to jump in?
Hi, thanks a lot, Sam, for the insightful things that you need to consider for camera trapping. So, I mean, just curious how you are planning to solve all the issues that you mentioned with Instant Detect, and also some specifications like the processor and the image sensor used in it. Thanks.
Yeah, great. Thanks for the question. I was trying to avoid plugging Instant Detect today, but I guess
you're fine.
I guess I can tell you that we've put in a really good low power processor in it, which has a very quick wake up speed. It's got a lot of processing overhead, so you could put in detection algorithms and image recognition things when they're developed. And we've just really focused on, first of all, trying to, with that there, we've then really focused on trying to get all the other parts of it working as well as a commercial camera trap. So the sensitivity of the passive infrared sensors there, that's well mapped to the field of view. The image that is taken has got a good exposure times. We've even got gain on ours, so that's like white balance, so you can tune it right down to very low light levels. All these little factors really that make up a really decent cake we've been trying to put into it. So yeah, we've been doing our best, and it takes time. We've been doing this for a long time. Does that help answer any questions?
I think so. So I've got some other questions. Paul wanted to know: have you assessed microwave radars versus PIR for motion detection?
Yeah, well, I mean, our camera actually has an external triggering connector port, so you can trigger it from any external sensor that you can create that will do a like a binary yes/no detection. So we've focused on a metal detecting sensor because we want to use this for detecting poachers with guns and snares and axes and what have you, rather than detecting animal motion and heat. But you could put in pressure plates and that sort of stuff. In terms of radar or LiDAR, I have looked at it, but it's a really expensive thing compared to a passive infrared sensor. So, we're trying to make this thing affordable, which is key for us, I guess.
Sorry, muted myself. Ariel, do you want to jump in?
Yes, hi, can you guys see me, hear me?
Can.
Okay, yay. So I'm really curious about image transmission, because I think it's important to keep people from repeatedly going into really sensitive areas. So have you built image transmission into your cameras?
Yeah, should I put my video on?
Yeah, please.
Yeah, sure.
Do that. Does it come on?
Yeah, I can see you.
Okay, great. Good. Yeah, we have put image transmission in our cameras. What we've done is we use a central base station which has satellite transmission capability, and this then connects to a whole load of cameras around it using LoRa, which is low power, long range radio, from the cameras to that base station. And that way you only have one, satellite airtime cost, because you're only paying for one, satellite airtime channel, but you can have multiple cameras all sending to this base station at a time. And so, I mean, our base station will listen to 8 cameras simultaneously, and then it will queue up other cameras if they're all trying to shout at once. It prioritizes them. But the key things here really are, how do you choke this transmission pipeline? ideally you'd send every single image, but as camera trappers will attest, you can get 800 captures a day on one camera, which is way too much airtime to send stuff. So we've really sort of focused on software controls that will choke down the number of images and make that intelligent for people and easy for people to understand. And really just the sending the data is kind of the easy bit. Once it's trying to refine what data to send.
What country are you in?
UK.
Your cameras are in the UK?
Well, I mean, we're going to commercially make this available worldwide at some point. Initially, they're built for the UK region 2 ISM bands.
Okay, cool, thanks.
No problem.
Rob, you had a question that follows on quite nicely from that. Do you want to jump in?
Yeah, hi Sam. My question was just about how well you're doing compressing your images, because we work with satellite data here and we get stung pretty heavily for very, very small amounts of data. So how are you going on that front?
So first of all, we have to send the images through the LoRa system. So for that, we compress them down. It's actually a percentage of compression. So you can set that however you want. But let's say that most images arrive and they're between 25 to 50 kilobits in size, kilobytes. And then when it gets to the base station, that's zipped up and it's sent over the satellite link. We're working with Iridium, and they're a partner for us. So actually, we get a very competitive rate with them because they support us with this application of it for conservation.